All right, in this video, we're going to begin section 12.3, which is derivatives and integrals of vector functions. All right, so first, let the capital F of t be the vector with components f sub 1 of t, f sub 2 of t, and f sub 3 of t. Where f1 of t, f2 of t, and f3 of t are differentiable functions. Then the derivative of the vector function, so the f prime of t equals, you just take the derivatives of the individual component functions, but you still have a vector. So f1 prime of t, comma, f2 prime of t, comma, f3 prime of t. So taking a derivative of a vector function just boils down to your ability to take derivatives of functions as you've been doing in the past and then just putting that in a vector. And then the derivative rules that you're accustomed to from Calculus 1, there are analogs for those things in Calculus 3. I'm not going to go through and write them all out in the notes, so I'm just going to refer you to the textbook. So you can see page 767, theorem 1210 for the sum/difference quote unquote product and quote unquote chain rules. Now these are not the sum, difference, product, and chain rules that you learned in Calculus 1, because in Calculus 1 you learned those for functions like these, for scalar functions. Now, like say for instance for the product rule, they're going to be considering two vector functions like f and capital G, and give you a product rule for that. Same thing with chain rule, same thing with sum difference rule. So these aren't the rules that you have already seen. It's just them translating it to vector function, And remember, for vectors, we have two products. We have a cross product and a dot product. So they're going to give you two product rules there. All right, next, I'm going to put a little note here, and it's an important note, and I'll stress it again in a later video because I'm not going to use it that much here, but you may see it in some example. I'm not going to use it in this particular video, but I will use it throughout the course, and you may see it in some examples. So if the vector function f of t traces out a curve C, then the derivative f prime of t, and remember this is still a vector, so your f prime of t is still going to be a vector, so it has a magnitude in the direction. F prime of t points in the direction of travel. at time t. So when I say points in the direction of travel, what do I mean by direction of travel? Remember when we have some vector function tracing out a curve C, we always put arrows on that curve C to indicate the direction of travel of whatever it is that we're discussing. So that's what I mean here, that the f prime of t is going to point in the direction of travel at any time t. And I'm going to sketch a picture of this after I finish the explanation. So now I'll explain how do you represent that visually. So when the tail of f prime of t is placed at the tip of the position vector f of t, f prime of t is tangent to the curve C. And hopefully this picture will clarify this. Now I'm discussing this now just because we've introduced the derivative of a vector function. So I kind of want to give you an idea of what that is. Same as when derivatives were introduced to you in Calculus 1, you wanted to get an idea of what that was that you were finding when you were finding the derivative. All right, so let's sketch some curve. Let's sketch some curve in 3 dimensions. So let's say you don't have to sketch your curve exactly like mine. I just want to have some portion of it close to the origin. So let's say this is my curve, and I'm going to come behind the y-axis, come back up, and let's say it does this, whatever. So there's our curve. Now, we have to have a direction of travel on here, so let's put some arrows. I'm going to leave this area blank because I'm not putting any arrows right here because I'm going to kind of sketch some other things there, and I don't want the arrows to get in my way. All right, so this will be my vector function f of t, and it's tracing out this curve C, so this will be my curve C, excuse me. So let's just label this C. Now my vector function at any time t is tracing out this curve. I'm not going to draw f of t a bunch of times, but what I want to do is I'm going to draw an f of t just at some particular time t. Let's say right here, because I want f of t to be a position vector. And position vector means, remember, vectors can move wherever they want to. So this is, I'm going to put a number in there just for sake of understanding. So if this is time, this curve is going on forever. So let's say this is time, whatever, 3. So that's that vector right there is f of 3. According to what I was talking about here, I want the position vector. Now I could take this vector and I could move it. I could draw it over here if I wanted to, but it's not a position vector unless I have its tail is at the origin. So I want to make that a position vector, and then I can draw f prime of t and also f prime of t, whatever I get. So I had some function f of t that gives me this curve. If I take 3 and I plug it in, it gives me the vector right there. Say, for instance, I take whatever. If I took 1.76, it might give me a vector that points right there. If I took f of negative 17, it might give me a vector that points right there. So the vector is tracing out this curve as you plug in values. So I'm just pretending that when I plug in 3, it gives me that point right there. So it points from the origin and gives me that. Now what I want to talk about is what is f prime of 3. So I'll take my f of t, take its derivative, which will give me this vector. Then I plug in 3 for all of those. So now I have some new vector. I could draw that new vector anywhere I want to on here. But this explanation here tells us that that vector is going to be tangent to the curve if I draw it. If I take it and I put it right here at the tip of this vector. So I didn't pick the best place in the world. So if I drew that right there, that would be my f prime of 3 is tangent to the curve, and it points in the direction of travel at that time right there. At that time right there, the direction of travel is that. Now, if I were to look at some new time right here, the direction of travel will be that way. If I were to look at the new time right here, the direction of travel is that way. So the direction of travel is always given by taking a vector that is tangent to that curve, and it's going to point in the direction of travel at any particular point. Now, you don't see the strength of f prime of 3 unless you are visually, unless you put it right there at the tip of whatever f of 3 is. Because I could draw f prime of 3, say down here, for instance. That does me absolutely no good down there because I really can't tell what information it's giving me. I can only tell when I put it right there. So let me see if I can find another one to draw a little bit better. So let's say I did, again, I went and I drew some other vector. So this is, if this is f of 3, whatever this vector is has to be sometime before the time 3. So let's say this is f of negative 2. Then I would take my vector function f, take its derivative, plug in negative 2. If I plug in negative 2, it's going to give me a vector. Now these lengths are probably incorrect on my vector, but don't worry too much about that. F prime of negative 2. And it points in the direction of travel because this vector right here is tangent to the curve and points in the direction of travel. And notice I want to draw this right there. I could draw this from the origin right there, but that doesn't help me. So it tells me at the time negative 2, my direction of travel is that way right there. Now, of course, negative 1.9999, then my direction of travel would move a little bit. So it only tells you at that particular time right there, and that's it. All right, so now the next thing, we'll talk about velocity, acceleration, and speed with respect to position, and then from there we'll do some examples. So now that we know how to take a derivative of a vector function, given a position vector, r of t, for an object its velocity vector is v of t equals r prime of t. Its acceleration vector is A of t equals v prime of t, or r double prime of t. And the speed of the object is the length of the magnitude of velocity. All right, so now I was talking about visually in that last part what we have with the derivative, but still the derivative is still rate of change as it has always been. So the velocity is the rate of change of position, acceleration is the rate of change of velocity. And now we know how to compute those things given a vector function. All right, so I'll stop this video here, and then the next video I'll talk about integration of vector functions, and then we'll do some examples.